Hi. In this video, we are going to learn how to perform analysis of turbine. This is a Pelton wheel turbine uh, which produce energy by the dynamic pressure of water. So this is a 2D analysis of Pelton wheel turbine. So this analysis can be done by two methods. One is UDF, that is user-defined function in Ansys, and another is giving 6 degree of freedom dynamic mesh. I'm going to perform this analysis with the 6 degree of freedom, as this method gives you the proper analysis, because we are not forcing the geometry to rotate in our defined way. Here the geometry will rotate according to the forces. So that is why this analysis is more accurate than user defined function analysis. So this is the geometry of the turbine. This is two surface. This is internal surface, which the whole surface will rotate, and this is out outer surface. So why do we need to create these two different surface? Is because my this outer surface mesh will only deform, while my inner surface, the whole this surface will rotate. So that is why I need to create these two surfaces to give different dynamic mesh properties in the Ansys. So now let's go to Ansys. Import your geometry here, then geometry to mesh. Now let's go to mesh. So in the meshing, there is a like, if we are going to give this a dynamic mesh, then it is advisable to do the tri-diagonal mesh instead of the quad mesh. So if you keep it default mesh, then it is going to give you a quadrilateral meshing. But as this mesh is like deforming mesh, we need to give triangular meshes. So this is my mesh size and configurations. Well, I would suggest you to give inflation layer around this wall as well, because as this is the wall and high velocity water will be striking through this wall. There will be many boundary layer phenomena. So to give accurate analysis, we need to create this inflation layer around this. Another things are, this two uh, boundaries will be my inlet. This is my turbine wall, and this one is outlet. This is my target surface. This is my source surface that you will see in dynamic mesh. Another thing we need to change is the context. So by default, it will give you very bizarre context that will be like connecting this surface to this surface, that we really don't want. What we want is this edge surfacing. I mean edge connection contacts. So we need to give the context between this edge and this edge. So delete the inbuilt context that you might have got from the meshing tool itself. Delete that and give this a new context. That's about the meshing. Another things are, you can give your meshing as you want, no, but not that much coarse, because this is again a dynamic mesh. So high quality is always recommended. And yeah, that is pretty much it. My average quality is here. So this skewness should be as close to zero as possible. But my maximum is this, minimum is this, and my average is this much. So that is okay quality mesh, not so good, not so bad either. So now let's go to the Fluent. So in the Fluent, as this will be a transient mesh, transient, I am not activating gravity because it's fine. No multi-phase. We are not now. We are not concerned about energy, because this is only a Pelton wheel turbine. So there are no phase change, energy change, no temperature changes. Ideally, but it's fine if you don't want to keep it. Don't keep it. Want to keep it. So the viscous model is K epsilon model with a standard K epsilon enhanced wall treatment. Well, you can try with uh, RNG and some other things, but this is very well recommended from my side. Then you can perform this analysis from water or air liquid as well. I'm going to perform this analysis with the water only. So this is fluid type, and this is water liquid. In the next there is boundary conditions. So in the from the inlet I'm going to give 25 meter per second water inlets from this both of these sides. Well, actually in these calculations are very complicated, that where you should keep your inlet inlets, what should be the numbers of your inlets and which angles, and these all things are very complicated, and this all needs to be calculated. But I am just going to give you idea about how to perform the dynamic mesh analysis. uh, these all things you can learn in many books of fluid machineries. I forgot the name of the authors. So here it is. The other boundary conditions are outlet. Those are pressure outlets simply. This is turbine wall. That is also a wall. Surroundings. Let's keep it as default wall. This will be my interior, and this is that interface that we created in the meshing tool. Now let's go to dynamic mesh condition. Turn on dynamic mesh, smoothing, layering, remeshing. In the settings, turn on the diffusion. By default, it will be spring, Laplace, and boundary layer. Now here we need to go through diffusion. Then in layering, you can decrease the split factor and this collapse factor as well, but the default settings are also good enough. In remeshing, what you can do is you can redefine this maximum length scale to maintain the quality of the mesh. You can do it with the 0.002 as well, but I did it with 0.003. It is fine because sometimes if you keep it to 0.002, it will take more time to remesh, and still it might not give you the accurate result as well. This is just like you know blind guesses as well, if you want to say, because no there is no proper accurate method to know that my which mesh size will do the most accurate analysis. So that is what you can do in this option. Turn off 6 degree of freedom. In settings, create a new this 6 degree of freedom. After you create, you will open this, give it the name anything you want, then calculate the moment of inertia. I gave it 0.004. I calculated this moment of inertia from Annex tool itself. You can also do by that tool, that is the tutorials are available on the YouTube as well. So this is 1 degree of freedom rotation. So as our geometry is 2D, so I'm not going to, I won't have 6 degree of freedom, but it is still said to be 6 degree of freedom. That is fine. So 1 degree of freedom rotation. Then my center is 0, 0 because I created my geometry such way, and then click on create. If you want to give some preloading condition, that is necessary for starting load conditions in actual power plant generators, but here it's fine. So now create it, and I am writing my mesh motion history. If you want to write, you can also write, but that is okay, fine. Then in dynamic mesh zone, we need to create some zones. So first we need to create zones like this, that in my interior source, that is my this surface, that surface should be deforming. So that is interior source deforming. In this meshing option, smoothing, remeshing, and you can give here 0.003, the same that you gave on this like dynamic mesh settings. And in yes, my target surface, that is my this surface. So my this surface will rotate with the rigid body constraint. So my inner mesh will not deform in this zone. My mesh will deform in this outer zone only. My this zone will whole rotate in this way because of the forces of the water. So that is my target body. In target surface, I need to turn this on. This is rigid body, 60 degree of freedom turn on, and that should be passive because my this surface will be rotating because of the force that will be obtained by this edge. So my 60 degree of freedom passive is on, and my turbine wall, that is my this walls as we created in the meshing tool, and this is also rigid body, and this is also turned on as a 6 degree of freedom, but this is not passive, this is active because the force will be received by these walls only. So here you go, create this, and now initialize your solutions. Click on initialize. Yeah, that is fine. Solution activities. Save your solution at every some time, because after that you are going to go through all the steps where you, for the video or anything rendering like that. Keep your time steps around this only, because it is very high dynamic mesh analysis and very dynamic phenomena. The boundary layer phenomena is happening over here. So to give you more and more accurate analysis, perform this small time step. I'm going to give numbers of time step as 1000, and max concentration for initial 100 or 150 time step, that your solution will converge in 30 time step, but after that you might want to increase the time step to 45, and your solution will converge in 45 to 50 iterations per time steps. So let's continue. Yeah. So here I have done 171 time steps, and I have created the file of this. I just want to show you the maximum temperature of my processor when I was doing this analysis. So it is 86 degrees Celsius. I don't want to burn my processor out, so I'm stopping my analysis over here, and this is 170 time step. So at 170 time steps, uh, this is my analysis, and to render a video I can show you. I go to animation, time step animator, go to this 0th time step, save movie, and you can see some the following steps in my previous video as well. So do this, and you will have a nice video. And here this video is for 1000 time step that I did on my different PC. So in this video, let me play it. Though it looks very good, but there is some problem associated with it. So as you can see, my velocity over here is higher than velocity over here and anywhere else. That is because we did not perform any calculations for geometry of this turbine. So my inertia of this wheel is actually lower than it should be to give you the proper power output. But anyways, this is just a tutorial to how to perform dynamic mesh analysis, so that is fine. uh, if you like this video, I will try to upload a new video every week, and bye bye.